So welcome everyone to the last session of the Categories and Companions Symposium. So first we'll hear from Dirk Hofmann, who'll be telling us about topology through the eyes of enriched categories. So please take it away, Dirk.
Okay, so at first, thank you. Second, thank you very much. I would also like to thank the organizers for this invitation. It's a great pleasure for me to talk here, and I hope it will be interesting to you. What I want to talk about is a little bit an overview of some of the work we have done over the past years, which was particularly dedicated to study topology, but as my title suggests, topology viewed through the eyes of enriched categories. Now, I mentioned already that I used the plural we because this work is based on collaboration with several people. I have here made a list of some of them. Not everybody was involved in everything, but everything I say in the sequel is collaboration with other people. Maybe I should also say right away that if you have any question, please ask right away, because it's always difficult with Zoom because I only can talk to my wall. So I'm happy if you ask questions right away. Very well, so let me at first try to introduce what it is all about. And the main motivation for our work is some relatively old result of Michael Barr, who describes topological spaces via ultra-filter convergence. Now, this is not really a new topic, but the description of Michael Barr I find particularly interesting, particularly elegant, which is the following. With U of X, I denote a set of ultrafilters and ultrafilter convergence relation, so a relation between ultrafilters and points, is the convergence relation of a topology, precisely if these two conditions hold here. So the first tells us that the principal ultrafilter must converge to the generating point, which we might see as an incarnation of the reflexivity axiom. And the second is we can see as a generalization, as a version of the transitivity axiom of an ordered set. So it says if we have an ultrafilter converging to a point, and if moreover we have an ultrafilter of ultrafilters converging in some sense to this ultrafilter, then the so-called diagonal ultrafilter of the big X must also converge to X. So if you ignore for a moment ultrafilters here and think that every entities are just points, then you see that this is just the transitivity axiom of an ordered set. So in this sense, we think about topologies as generalized orders. There's a slight technical difficulties, which lies actually here. We have to talk not only about convergence of ultrafilters to points, but also then of a convergence relation between ultrafilters of ultrafilters and ultrafilters, which means we must apply the functor U, the ultrafilter functor, not only to functions, but for instance also to this relation. So we need some sort of extension of the ultrafilter functor to relation. Now, this description motivates that we want to develop topology, topological results and notions as topologies would be ordered sets. And what I want to try to explain today is that nevertheless we will reach at some traditional topological topics, which I will explain on the next page, but through the path of enriched categories. So for instance, we will naturally recall and reach a description of exponential topological spaces, meaning those topological spaces where a product functor with X has a right adjoint, and they were characterized in the 70s in Australia actually by Brian Day and Max Kelly as precisely the core compact spaces. Core compact is a slight generalization of locally compact. Actually, for sober spaces, which is another special topological notion, it means that every irreducible closed set is the closure of a possibly unique point. Then core compact means exactly locally compact. Another classical topological notion we want to visit naturally via this path is that a topological space is an injective space if and only if the topology comes from a continuous lattice. And this is a classic result of Dana Scott, also from the 70s. Another important notion which I would like to mention is, which goes back to Leopold Nachbing, is that of an ordered compact Hausdorff space. That is a way to join order theory and topology. More concretely, it is a triple where we have an order relation and topology, more concretely a compact Hausdorff topology. And these two structures need to be compatible by what I indicated here. The order relation should be closed in the product topology. And as I mentioned already, this goes back to Leopold Nachbing in the 50s. We will also visit the filter space of a topological space, which is the space of all filters of the lattice of opens, and the Viatorius space, which is topological space built on the set of all closed subsets of X. And in this context, we will visit an old result of Oswald Wheeler, characterizing the algebras for the Viatorius monad. Here we have already that this construction is actually part of a monad. Considered on compact Hausdorff spaces are precisely the continuous lattices. So these are some results I will visit during this talk. Now our path to this is not motivated by open sets, like traditional topology, but is more motivated by convergence and more concretely by order theory or category theory in general. So maybe I would want to recall next some notions of order theory which will be relevant in the sequel. Okay, at first, maybe I recall that the category of ordered sets, unlike topological spaces, is Cartesian closed. Maybe I recall here quickly. Try if it works. I hope you can see now the whiteboard. Yes?
Yes.
Mm-hmm. Oh, okay, thank you. So let me recall that this means that the functor product with X has...
Could I ask a question quickly? When you say ORD,
yes, please.
What are usually called pre-ordered sets for a lot of people, right?
Ah, yes. I haven't made it clearly because in the context of categories, we consider ordered, or as an ordered set, I only mean reflexivity axiom, which we can think of as the identity axiom of a category, and transitivity, which we can interpret as composition law of the category. But in general, I do not assume antisymmetry. In fact, that doesn't make a big difference. Sometimes one needs to be careful with unicity. Okay, either way, Cartesian closed, we refer to the product functor, has a right adjoint. Which is typically denoted like this, like function space. And more specifically, if you take another ordered or pre-ordered set, this, the function space, is of course defined as the collection of all monotone maps from X to Y. Well, it should be an ordered set, so we have to explain how it is ordered, and generally one defines it via the pointwise order. So we would make now here that F is less or equal than G, being two elements of y to the power of X, whenever we have for all X in X, F of X is less or equal than G of X. Yeah, and one can then prove that this construction is right adjoint to this here. Now, in order to do so, it is slightly more convenient to describe this order relation slightly different. So let me add here. One might equivalently say that for all X and X prime in X, if X is less or equal than X prime, should imply F of X is less or equal than X prime, F of X prime. It is not hard to see that is both conditions are equivalent. but this one is a bit more useful in the proof of the fact that is the right adjoint. And why is that? Well, part of the proof will require to show that the evaluation map, which will be the co-unit of the adjunction, which takes a function and a point and evaluates it, this should be a monotone map. So we need to equip this with a structure, making this map monotone. In fact, in order to get the exponential, we need to equip it with the largest such structure. So we might know, I hope it fits still. Now the structure on the product is defined by the structure we want to define here and the structure on X. So we would define now here that F is less or equal than G, having two elements here. Well, if and only if it does not contradict that this map is monotone, which means this should be the case. So this we want to define. Now we can see whenever we have some order relation here, so you see this condition, which then, if this is less or equal, would give us something here, which then, in order to that be monotone, should be in order relation here. So we will see that for all such, we should have now that evaluating f and x and g and x prime should result in f of x is less or equal than g of x prime.
So,
which,
yeah,
of course, you see that I made a little mistake here. It should have been
okay,
g.
cool.
Now, so this is the largest structure to which allows, which makes this map monotone. So even if it's very easy, I would like to quickly discuss one of the properties we need to prove now is that this is transitive. So we would now want to have that whenever is f less or equal than h is less or equal than g. Maybe for a second, since this is written here, I erase this. And maybe this one I write quickly here. That we have now f less or equal than h less or equal than g. So we would want now to get that f is less or equal than g. So following now this idea, we need to give us a point here, which I write now, and maybe I use already the convergence relation, is less or equal than x double prime. And we need to get to the conclusions, and then f of x is less or equal than g of x double prime. And maybe you see now it would be useful if it would be always possible to find something here in the middle, which now, because we know that this is true, would give us an h of x prime, and we have here a less or equal, and we have here a less or equal, and since we know that y is reflexive, we get a less or equal here. So the point is, in order to prove that this works, we need to show that in an ordered set, maybe write it here explicitly again, whenever we have x is less or equal than an x double prime, there should always exist something in the middle, which is always true in an ordered set, because we can choose this point x, either this, or many other options depending, but this two we always have. Now I mention this because if we pass to topological spaces, a very similar proof would work. Just we have now to consider here a function, we have to consider here ultrafilters and points and possible ultrafilters of ultrafilters. And we have to consider here a function, an ultrafilter of functions, and an ultrafilter of ultrafilters of functions. So eventually, trying to follow the same proof, it should change the page. And just a second. No, it did. So we would have for X topological space, we would now get that X is exponential if and only if we have the same property that something always exists in the middle. So let me write now for an ordered set. It would again mean that whenever if X, let me call it for a second Y, if Y is in relation with X, there exists something in the middle. Now for a topological space, this Y here is not another point, but it's actually an ultrafilter of ultrafilters. So this big X is an ultrafilter of ultrafilters. And we would take its diagonal filter. So whenever the diagonal filter of an ultrafilter of ultrafilter converges to a point, this should imply that there exists something in the middle. So this should exist, which unlike for ordered sets, it's not always true.
What do you mean by the diagonal ultrafilter?
It means that we have to reduce the ultrafilter of ultrafilter to an ultrafilter. Technically, it would mean that M of X, it's the multiplication of the ultrafilter monad. So this is an element of U of X, so an ultrafilter of ultrafilter, and one would define it as the union over all elements of X, which is now a set of ultrafilters, and then the intersection of this A. Sorry, wrong letter. So then M is a function which reduces an ultrafilter of ultrafilters to an ultrafilter. Maybe just try to keep this idea. We reduce an ultrafilter of ultrafilter to an ultrafilter, which can then converge to X. And then we get again such a condition of there must exist something in the middle. And then one can convince oneself that this condition here in fact means core compact. I use this example to show a bit that an intuition which comes from ordered sets can be used also in the proof of something of topological spaces. It is technically a bit more difficult because instead of with points, we have to deal with points, ultrafilters, ultrafilters of ultrafilters, and possibly more levels. So maybe to write this down, this condition is in fact is equivalent to X is core compact, which once again is a slight generalization of locally compact. Okay. And return to the slides. So in ordered sets, this condition is always true. So ORD is Cartesian closed. I also would quickly mention that ORD is actually a two-category in a very trivial way because monotone maps we can compare pointwise. I just mention this because it of course allows us to talk about adjunctions, which later on we will also do in topological spaces, which is maybe not such a classical notion. Another important notion I quickly recall is that to develop order theory, we often also make use of not only monotone maps, but also monotone relations, which are called distributors, which once again, it should be thought of as a relation which is compatible with the order relation, which can be expressed, for instance, by saying that the corresponding characteristic map is monotone of that type. A particular instance of a distributor is the order relation itself, which is in fact a monotone map of this type, where we have here the dual ordered sets. And this fact gives, or one can see as a starting point to talk about complete and co-complete ordered sets. Using the fact, for instance, that ordered sets or partially ordered sets or pre-ordered sets, it doesn't matter here, is Cartesian closed, we can use its mate here, which is the Yoneda map, and we know that this is a monotone map. Then it is also known that an ordered set is co-complete in the sense it has all suprema, if and only if this map has a left adjoint, which calculates for each down set here. You can think of the elements here as down sets of X. It's supremum. There's another useful notion that of constructively completely distributive, which can be expressed by saying that this left adjoint has a further left adjoint. You can also think of it that it means that the supremum map is right adjoint, which, since we have now here complete ordered sets, just means it's compatible with infima. So this condition expresses in some ways that suprema distribute over infima. And there is a result of Richard Wood and Bob Rose's book, which I just want to mention here, that the category of SUS lattices, of completely distributive lattices in submaps, is equivalent to the idempotent split completion of the category of ordered sets and distributors. Now in ordered sets, we can move to the dual and somehow develop kind of the same picture, which I have summarized here quickly. Of course, instead of moving this to the other side, we can move X to the other side and then also the dual. So we get, which might be seen as the dual of the Yoneda embedded this map, and this leads to the notion of limits. So the ordered set is complete if this map has a right adjoint, and it is a kind of dual of completely distributive if this right adjoint has a further right adjoint, which can be also expressed by saying that infima distribute over suprema. I didn't write it down here, but this dual notion of completely distributive, but at least in classic mathematics, is equivalent to completely distributive. And we have a similar result to this one. And I've given here some references, which at least I found very helpful for developing order theory using adjunctions. But what I will want to do a little bit later, hopefully not too late, is to kind of try to do exactly the same, but for topological spaces. And we will see that creates some technical difficulties, but it does then lead to also to some classic topology. But let me go on a bit with order theory, and let me quickly have a view at suprema from this point of view of distributors. And let me at least first recall that for any monotone map, we can associate two distributors, one going from X to Y, so a monotone relation from X to Y, which I denoted F lower star, and one going from Y to X, which I denoted F upper star. And they are defined like this. The first one says that X is in relation with Y, if f of X is less or equal than Y here, and the other is defined somehow dual. Let me also recall, I mentioned it already, that the distributor from X to 1, which is a relation, a special relation from X to 1, which we can view as a subset of X, and being distributor means it's a lower subset, and being a distributor of Z type means it's an upper subset. Now let me quickly talk about suprema. So typically we would say would define a supremum of a lower subset of X, so which I have written here as such a distributor from X to Y, and here I have written the order relation. Now, normally we would say to calculate the supremum of a lower set, we take the upper set of all upper bounds and then the smallest element of this, which in the language of distributors can be expressed like this. So we're looking for the upper set of upper bounds of X, which is a distributor of this type, which which I can write here. So this phi, this corresponds to the upper set of upper bounds of psi, which universally can be described as the largest distributor from 1 to x, such that composite with psi is less or equal or contained in the order relation. So this way we can describe the upper set of upper bounds, and then saying that there is a smallest upper bound means that this distributor is representable by a point. And this point we would denote as the supremum of x. So this can be seen as a kind of distributor description of suprema, which I will later use for topological spaces. Now, this picture can be a little bit or formally generalized without actually changing the notion of suprema. So for instance, instead of considering here the one-element ordered set, we can also consider an arbitrary order set and then describe the supremum, which I now call colimit, of such a distributor now as the function which represents this distributor. And we can also recall that the order relation on X is lower star of the identity. And instead of considering the identity map, we can also consider here an arbitrary monotone map, and then still define colimit in exactly the same way. A monotone map which represents this distributor. Now, co-complete would mean that all such suprema exist. And no matter if I take this notion of colimit or the original notion of supremum, it's equivalent. So if all this suprema exists, then also all these colimits exist. For ordered sets, it doesn't matter. For topological spaces, it will be slightly different. Okay, that was about order theory. Now, another motivation for us was an observation due to Lavier that also matrix spaces can be seen as generalized categories, which can be found in the paper I indicated here. And I have written here in comparison the axioms or some of the axioms of a matrix space, which says that self-distance must be 0, and the triangular inequality, which we can see as generalizations of the reflexivity and the transitivity law of an ordered set, or if you wish, as the identity law or the composition law of a category. Now, besides matrix spaces, we can also consider ultramatrix spaces, where in the triangular inequality one would substitute plus by max. And hence also matrix spaces can be studied as categories, or if one is more modest, as generalized ordered sets. Now, one of the big discoveries of Bill Lavier was that into these pictures one can nicely describe Cauchy-complete matrix spaces, which I would recall very quickly. At first, in the context of matrix spaces, we would now define distributor as a non-expansive map of this type. I wrote here infinite to 0 because we should think here as 0 corresponding to true and infinite corresponding to false. So infinite is kind of the smallest element and 0 is the largest element. Now, Bill Lavier observed that a Cauchy sequence in X can actually be described by a pair of distributors. More generally, assuming just a sequence in X, we can define these two distributors. They are somehow defined via limits in this matrix space, and they denotes the matrix of X. I haven't written it explicitly. And then one can show that our sequence is Cauchy if and only if these two distributors are adjoint to each other. The other way around, every such adjoint pair of distributors can be seen as being induced by a Cauchy sequence of this type. So at the end, we will find out that equivalence classes of Cauchy sequences are in one-to-one correspondence with right adjoint distributors. or if you wish, with such adjunctions. And moreover, one can then describe convergence point as a sort of co-limit of such a distributor. And I have here written more or less the same diagram I had on the other side. Such a Cauchy sequence converges to X if, whenever I take the corresponding distributor, again, ask for the largest distributor, such as this composite is less or equal than the identity, which, by the way, must be Z1. And then we ask this one to be representable by a point X. It's representable by X precisely when this Cauchy sequence converges. So, without referring to Cauchy sequences at all, one can then define Cauchy completeness as saying that all such adjunctions are induced by a single point, or if we want to express it in terms of co-limits or suprema, if every distributor, every right-adjoint distributor has a co-limit. So this I also have written down here. A matrix space is Cauchy complete if each such diagram where our distributor here is a right adjoint has a co-limit, and if we take the space of all these right adjoint distributors, that also gives the Cauchy completion. I see already I'm way behind time. Let's continue. So we can also see here that matrix spaces can be studied as categories, or more modestly as generalized categories. So quickly to bring this under one roof, we consider usually the notion of quantile enriched category, which is a simplified version of categories enriched in a symmetric monoidal closed category. So technically a quantile is an ordered set which, viewed as a category, is symmetric monoidal closed. More concretely, it has a monoid structure, which is a monoidal structure such that tensoring with every element should have a right adjoint. And relative to such a notion of a quantile, we can now define category enriched in the quantile, where again you might see here the incarnation of the reflexivity and of the transitivity law, or as self-distance zero and the triangular inequality. And we would define V functor, well, basically as a generalization of monotone map. So if X is in relation of X primes, then the images must be related, for instance. And for future reference, the category of V categories and V functors we will call as V cat. As examples, we have the two I mentioned before. So if we choose as our quantile V the value set of proof values 0, 1 or false true, then V category means exactly ordered set or pre-ordered set. If we choose the quantile 0 infinite, with the order relation reversed to the natural order, so it's the greater or equal relation, and we choose as our tensor, as our multiplication by addition, then categories enriched in this quantile are exactly matrix spaces. That is the example of Lavier. And we can also choose as tensor the maximum, so the maximum of two real numbers. And in this case, categories enriched in this quantile are ultra matrix spaces. Another interesting quantile here would be if we don't take 0 infinite, but stop at 1, and take as tensor addition, but it must be now truncated at 1, so truncated addition. And in this case, categories enriched in that quantile, we could think of are bounded matrix spaces. So matrix spaces where the distance is bounded by 1. These examples under 2 and 3 can be also viewed differently, a different quantile. If we take the unit interval, take now the usual order, not the greater or equal order like here, and this tensor infimum, then categories enriched in Z quantile are ultramatrix spaces, so as we say in this example. If we take the ordinary multiplication of numbers, real numbers, then we actually get this example as categories enriched there. And if we take what is often denoted as the Lukasiewicz sum, it's defined like I wrote here. In this case, categories enriched in Z quantile is exactly that example. The advantage of this point of view is that we never have to change the letters. It's always 0, 1 with the ordinary order. But I would quickly, or not that quickly, mention still another example, a little bit more in detail, which stems from Carl Menger, introduced in 1942 as so-called probabilistic matrix spaces. He defined it as a matrix space, not as a matrix space, as a structure like I described here, which you should read like this. The value of dxt is u means that u is the probability that the distance from x to y is less than t. So in this case, we don't measure distances exactly, we can only know probabilities of the value. Now also this example fits precisely in the framework I just described. I started to write here the axiom given by Menger. It requires the function, if we fix the last, if we leave the last variable open, must be left continuous. Well, for every positive t, the probability that the distance from x to x is less than t must be always 1. This is some sort of triangular inequality, and also this axioms more or less correspond to axioms of classical matrix spaces. You see here the symmetry, and here he had the axioms that the distance should be always finite. Now, in order to capture this example, one can consider the following quantile. We take now as our set of points the left continuous function from 0 infinite to 1. And you can see here there can be defined a tensor product, which is a sort of convolution product. And the function which is 0, which at 0 is 0, if for every positive value is 1, will act as a neutral element for this tensor. And then we can essentially make the exponential transpose and move this to the other side. And then we can see that probabilistic matrix spaces means essentially categories enriched in Z quantile. So that would be another example of a category enriched in the quantile, which is worth studying. I only have 10 minutes. Before I get to the general notion, another motivating example for us is also a notion which is already around since the 80s. It's of so-called approach space, which you can think of its approach spaces are to topological spaces what matrix spaces are to ordered sets. So instead of defining, for instance, a closure operator, think of this map as a closure operator, we define the distance of a point to a subset. And it should satisfy the axioms I wrote here. There are several ways to describe these approach spaces, similar that there are several ways to describe topological spaces. I have here chosen the original one, which refers to a sort of generalization of closure operator, but one can describe it in terms of convergence. Now the convergence is not a relation, but let's say a relation with truth values in 0 infinite. So it's not that the ultra filter converges to X, yes or no. We have now a distance, how far it is away from being a convergence point. And the axioms are again exactly the same which we found before. It's the reflexivity axiom and the transitivity axiom, or the triangular inequality, if you wish. So what we wanted to do and did was to describe all these examples under one roof. So we would want to describe structures where we have some kind of categories taking value in a quantile, but the domain of our arrows, if you wish, should not be just x, so it's not a function from x cross x, but we would allow, for instance, ultrafilters or sequences or whatever here, so as a domain of our arrows. So more generally, we would allow here an application of a monad T, and we take here an arbitrary quantile, but we need a little bit more than that, because we then have to apply our, whatever our functor is we apply here, to this type of relations. And I should try to do a bit quicker. In order to capture all this example, we have come up with something which we call topological theory. So it's not a very good name, but it should indicate that is some sort of theory which models are topological categories of interest in topology. And maybe I'll go quickly over this. As I mentioned before, we want to consider a quantile. We want to consider a monad, which, for instance, could be the ultrafilter monad. And these two notions should be connected. And one possibility for this is to require that we have a map from applying our functor to the quantile, just viewed as a set, to the quantile. So a sort of T-algebra structure on our quantile. Now there come some technical conditions. Our functor should preserve V equal backs. Then in fact, this map should be an algebra structure for this monad. And moreover, the monoid operation in our quantile should be kind of Lex algebra homomorphisms. In fact, for many results, we will need that they are not just Lex, but really algebra homomorphisms. And that is the kind of starting point we want to work on to describe this structure. The first difficulties we have to pass is to describe how to apply our functor T, which a priori only applies to sets, to relations. And while that is possible, I have described it here. So we would want to have a relation. Maybe I describe it quicker here and then I jump over this. I hope it appears now. Just a second. So we have our functor from Z to Z. And we would want to apply it to a relation which is now of this type. So to this, we would want to describe a relation which we would call T of R, which should go from T of X cross T of Y to V. So how to do this? Well, we write what we know. We have this. Sorry, I should. And of course, we have the projection to T of X cross T of Y. Then we can apply, of course, here our functor T to R, which goes to T of V. Now just viewing this as a map. And here we have our algebra structure to V. And now the map we are looking here is the largest map, such that we have here an inequality. Sorry, not the largest, the smallest. So which we might recognize as some sort of comma extension. Okay. No, that's not what I wanted. Okay. So maybe now I more or less hold this here. Maybe I jump over this. Some notion I used already, for instance, in the example I just explained, is that of a V relation, which you should think of as a relation, as an ordinary relation, where truth values are not in 0, 1, but in an arbitrary quantile. And it is important to observe that this type of relations can be composed by the usual relational composition, or if you wish, it's matrix multiplication. But in our context, for instance, if we think of convergence relation, it will not be a relation from x to y, but from u of x to y. So more generally, I would want to talk about T relations, which, as I mentioned already, is a relation between, for instance, ultrafilters of x and points of y. And thanks to the fact that our T is part of a monad, we can compose this type of relations. So of such a relation, I still think of a general T relation from x to y, and we compose this type relations by Kleistli composition, or I wrote here Kleistli convolution, but it's in fact Kleistli composition. Let me mention here that at least if we assume our theory to be strict, this operation is associative, and the inverse relation of the unit of the monad acts as a sort of Lex identity. Well, and based on this notion, we can now introduce more general T category, which is now a generalization of how we define, or how Michael Barr described topological spaces. We can describe it via these inequalities, or we can use this Kleistli convolution and say that, well, essentially describes them as a sort of monoid. But point-wise, it means exactly what, for instance, we call the ultrafilter convergence description of topological spaces, or of approach spaces, for instance. A functor is essentially defined as a monotone map, or in case of topological spaces and convergence, as continuous map, as convergence preserving. But motivated by order theories, there comes another notion, which is that of a distributor, which now we define similar as for ordered sets. Just we use now Kleistli composition instead of ordinary composition of enriched relations, or of relations. So a distributor from x to y is a relation from, let's say, ultrafilters of x to points of y, which is somehow compatible with the convergence, for instance, or more general with the T category structure. And like that, we get the category of T categories and T functors, or the category of T categories and T distributors. Let me quickly mention examples. Of course, if we choose the identity monad, then we get the category of VCATs. If we choose the ultrafilter monad, and as algebra structure, well, 2 is a finite set, so U of 2 is the same, so we can choose it essentially as the identity. Then TCAT is top. We can more generally consider a completely distributive quantile in the ultrafilter monad, and then we can always consider this psi. This way, for instance, we also describe approach spaces. And we can take, for instance, the free monoid monad, and in this case, we get some sort of multi-categories, or in case of ordered of the two-element quantile, multi-ordered sets. Similar to for ordered sets, we can associate to each T functor a pair of distributors, which are defined very similar as in the case of ordered sets. And this gives us two ways to embed topological spaces, for instance, or in general T categories, into the category of T distributors, which is very similar to the case of ordered sets. Okay, what I would want, or what we wanted, or what we did with this notion, now develop the notion of co-limits and the notion of limits, which, unlike for ordered sets, are not at all dual to each other. If I look at my time, I don't have time to talk about both, so maybe you can quickly tell me how much time I have left. Somewhat.
I think we started about 5 minutes late. So, I mean, we're almost at the 50-minute mark, but I think we can have another maybe 5 minutes, and then we can have some questions.
5 minutes. Okay, I stop in 5 minutes. So let me quickly to give you an impression about how we would now define co-limit, which is relatively easy because we can. Maybe at first I pass to this. Maybe you recall, in order to have, just a second, it switches. To define co-limit in an ordered set, we started with a distributor like this. Then here I write, well, it's essentially equality, so let me write it like this. And then we ask for the largest distributor, such that this composed with this is less or equal than this, and then ask this one to be x lower star. And then we would call x the supremum of psi. Now for topological spaces, we can do the same, thanks to the fact that this largest distributor also exists. Just now, instead of, we have to use the topological notion of distributor. So, coming back to the slides, we have to make sure that such a limit, such a lifting exists, but it can be constructed as a lifting of V distributors. So if we have such a distributor from T of X to Y, we apply our functor T, and here the opposite relation of the multiplication of the monad, and then we get a V relation from T of Y to Z, which is then a T relation from Y to Z. So the point is that this type of lifting exists. Since I won't have time to talk about it later, let me mention already that the dual notion of this type of extension exists, but the dual notion of lifting, which we would need for limits, does not exist. Which is already one indication that limits in this context are not really dual to co-limits. So maybe let me quickly mention that we can now define weighted co-limit in TCAT exactly as in VCAT, just using now T distributors instead of V distributors. But there comes a little difficulty. I call X totally co-complete whenever it has all weighted co-limits. Now, why do I say here totally? Let me try to switch again to here and make this. No, it's this one here. If we define co-limit in ordered ordered sets, for instance, I mentioned that I can write here the one-element ordered set or an arbitrary ordered set, doesn't matter. For topological spaces, it does matter. So I would need to write here an arbitrary topological space and require all these co-limits to exist. Now this should be represented by a map. And I would use the notion of what talk about co-complete if I restrict to the distributors where here is the one-element set. Let me also say that we can introduce Cauchy-complete by requiring only co-limits of right adjoint weights. And just to explain that it doesn't give anything weird for topological spaces, then a topological space is totally co-complete, precisely if it's a continuous lattice. So it leads us naturally to that notion. And a topological space is Cauchy-complete, precisely if it's weakly sober. Right, maybe to shorten, let me jump over the next page, I hope. And maybe just slow. Come to some further result about co-complete. We can define some sort of Yoneda embedding, which indeed you might recognize here. It's some sort of Yoneda lemma, it just introduces now an element of Tx, and you can actually get.
I think your screen.
Sorry.
Yes, it is for me.
I didn't switch properly. Now you can see. Sorry. We can define some sort of unit.
We're almost at the end. Probably one.
Yes. This is the last page. Just maybe to mention that we do get a sort of pre-sheaf monad on Tcat, which generalizes the pre-sheaf monad of categories. And the co-complete ones we can identify as precisely the algebras for that monad. So technically it has some more difficulties which I couldn't mention here. But we can repeat a little bit the picture which exists for categories and reach a notion of co-complete topological spaces, for instance, which reduces, in case of topological spaces, to the theory of continuous lattices. Just to finish, I only mention or repeat that if we want to talk about complete ordered set or complete T categories, that is technically a bit more difficult because several results we have for ordered sets or V categories do not work in this case. And in fact, it will not be the dual notion of co-complete. In particular, we don't have that the topological space is totally complete, even only if it's totally co-complete. But I must apologize for the time management. My time is over, so I stop here and thank you very much for listening. Thank you very much.